So I suggest we start by the introduction, but in fact, I don't know where to start with the introduction of Leyffer, because Leyffer is a very, very long and impressive community. He is currently at Argonne National Laboratory, and is one of the most famous current researchers in optimization. He has many, many contributions in nonlinear programming, mixed integral nonlinear programming, robust optimization. He has obtained he has reached many achievements. And we only cite two achievements, but it highlights the quality of his works. In 2006, he received the Lagrange Prize in Continuous Optimization from the Society of Industrial and Applied Mathematics. And in 2016, so 10 years after, he received the Farkas Prize from the Informed Optimization Society. So just as a two well-respected prizes, among the highest prize in optimization, are sufficient to underline the quality of Sven Leyffer as a mathematical optimizer. So it's a great honor and a great pleasure to have him with us today. The last talk, I hope that you have enjoyed the workshop to that. So, but this is already the last talk, but definitely not the least one. And so we have the pleasure to hear Sven Leyffer. In fact, we have even two talks for the price of one, because he will first speak a bit about simple linearization ideas for nonlinear robust optimization. And just after, he will speak about derivative-free optimization under uncertainty for high-energy physics applications. So I'm very eager to listen to you, and the floor is yours.
Thank you very much, Fabian. That was a very kind introduction, far kinder than I deserve. I should also apologize to everybody. I was going to talk about a sequential linearization approach for nonlinear robust optimization, and that work just didn't go as far as we had hoped. And I then changed tacks last night and decided instead to talk about an application, which is a derivative-free optimization problem with uncertainty that we're solving with some people at Fermi National Accelerator. But I wanted to give you at least also a little bit of an insight into where we're going with nonlinear robust optimization and what we're thinking of. This is a very simple idea. Well, I can summarize it in 5 slides. So if I'd just given this talk, you could all go home in about 15 minutes. And of course, you can still go home. If you don't like the talk, you can all go home early. So here's the problem that I'm going to look at in the first part. I'm going to look at an optimization problem where we have a nonlinear objective. There are some constraints that are deterministic, which I denote by the set X here. And I have one robust constraint, and the robust constraint has very special structure. So in particular, I'm going to assume that this uncertainty set on the right here is a convex set. And the uncertainty only affects this nonlinear constraint in an affine way. Everything I say here generalizes to problems where I have multiple of these constraints. So I can add a subscript I here everywhere, and it will just carry over. So that's not a loss of generality, the fact that I only have one. But key is really that the uncertainty set appears affinely in this problem. And it turns out with this setup, there are some interesting applications. So it's not just something that's pie in the sky. And you have some interesting, or there's an interesting new way of solving this problem that's very simple and easy to explain. So I'm going to dive straight into the trick. So you have this robust constraint here, and we've seen talks, very good talks about robust constraints already. So that's an infinite number of constraints. This set U is an infinite set, so you have an infinite number of constraints. And so the first trick that I'm going to use is I'm going to tighten this problem by looking at a polyhedral superset. So this set P is a set that includes my set U, but I can write it as an affine set. I can write it as a polyhedral set. And that turns out to be important later on when I do develop my algorithm. So I'm starting off with this tightened set, and then there's a little trick that everybody who works on robust optimization knows, which is you can go from a sort of infinite number of constraints for all U and P. You can go to this maximization problem here. So you simply say, well, and it's easy to see, if the maximum of this left-hand side here is less than or equal to B of X, then it holds for all U and P and vice versa. So that's a very simple equivalence. And the interesting thing now is we can now use some, again, very easy tricks to reformulate this problem. And in fact, there's this nice duality trick that's probably due to Shapiro and others back in the early days of robust optimization, where you introduce multipliers for these linear constraints here, which I call gamma. And then you can rewrite this maximization problem equivalently, provided it's feasible. So I'm making the assumption that I have feasibility here. You can write it equivalently as this minimization problem over here. And now I can take the objective that I was maximizing here and basically replace it by this objective. And now the trick is that because my constraints, my robust constraint was here, that I'm bounded from above by B of X. So if I can find any feasible point any feasible point gamma for which this holds, then it also holds for the minimum, because the minimum can only be smaller. So the left-hand side here can only be smaller. So what we just did was, this is a very simple trick. And what we just did is we started off with a robust optimization problem with an infinite number of constraints, and we ended up with a standard nonlinear optimization problem. It's finite dimensional. This is an easy problem to solve, provided you can somehow handle maybe the non-convexities that arise here on the right-hand side and up here. But at least for finding local solutions, this is a very quick way of solving this particular class of robust optimization problems. And our idea then is, and this is why it's just a very simple idea, to use this in an iterative algorithms where we iteratively construct these supersets. So we start off with some P0, some initial superset, and this could, for instance, just be a box that contains my uncertainty set U. And then I solve, on each iteration, I solve a tightened optimization problem, or the equivalent one, which is this nonlinear optimization problem. I can then obtain these multipliers gamma and the mu x, and from the gamma, I can reconstruct my primal solution to my uncertainty space. And typically, this will not be in the uncertainty set. If it is the uncertainty set, then I'm done. And if it's not, then I project onto the uncertainty set, I obtain a new point, and I can then use that new point to simply linearize my nonlinear constraints that define U. So that's my nonlinear constraints that define U, where G of U less than or equal to 0. So I can just linearize these constraints down here and add them to this polyhedral superset. And so that's the end of the story. And so if this was the content of my talk, you could now all go home. So we have a way of looking at a nonlinear robust optimization problem that has this very special structure where we have one or many constraints in which the uncertainty appears affinely, and we can define a polytopic superset and iteratively refine this superset. So the nice thing is that we solve a sequence of robust optimization problems without having to solve a sequence of robust optimization problems, because they're equivalent to nonlinear standard nonlinear optimization problems. And we're looking currently at applications. So the portfolio optimization problem can be formulated in this way. And in particular, it allows you to have more interesting uncertainty sets here that maybe you couldn't handle with equivalent reformulations. And we're also looking at a robust tracking problem for optimal control. So this is, as you can see down here, this sort of concludes my talk with 6 slides, very short talk, very simple ideas. I should say I'm very happy to take questions during the time. The easiest way to ask questions is not to raise your hand, just to start talking. And I'm locked in, I'm wired for sound, so I'll hopefully hear you. So you can ask me questions later about that, or you can ask me questions now. If there are no questions, then
I have a question.
Oh, go ahead, yes.
You invited questions. So what do you mean by tractable subproblems, given that your subproblems all have like nonlinear equality constraints?
Right, so that's a good, excellent question. So tractable, I mean, I can find local solutions. So, okay, that's maybe not, my idea of tractable here is I can use IPOpt or filter SQP or SNOpt to solve these problems.
Okay.
And you're right, that's not tractable. Let's correct that right away. Sorry. There we go. It's not tractable in the sense of complexity theory. So that's a good observation. Thank you. Okay, so with that, we say to all of those who are not interested in derivative-free optimization and uncertainty, have a wonderful weekend. Thank you for coming to this wonderful workshop. To those who are staying here, I apologize again for tricking you into listening to a second talk. This is joint work with a postdoc of mine, Mohan Krishnamurthy, who's actually moving to Canada, but he'll continue to work with us. So he just got his Canadian residency, and he'll be up there in Toronto, I believe. So here's the outline for the remainder of my talk. I'm going to introduce this problem in high energy physics that involves event generators. And this is a very important problem that a lot of CPU hours are spent on solving this problem. It's basically a problem for finding parameters that explain the physics underlying certain high energy experiments, such as the Large Hadron Collider. And I'll talk a little bit about different types of approximations that we can use in order to solve this problem. And we have started with Mohan, we have started to look at a trust region framework for solving derivative-free optimization under uncertainty. And this is very much work in progress. And so I'm open to questions. I'm also open to suggestions and ideas. Or you can just listen to my talk, have your own idea, and then go away and develop it yourself and scoop us. That's also possible. So here's a short introduction into Monte Carlo event generators for high energy physics. These are very sophisticated software packages that simulate in order to predict the properties of high energy particle collisions. And they're sophisticated in the sense that they even take the length of the wires that the detectors have into account in some cases. So they're very sophisticated software tools. They describe probabilities for sub-event phenomena, so they often collect counting statistics, and they allow us to bridge the gap between particle physics perturbation theory, which is at very high energy scales, and the observed subatomic particles at low energy states. So we're interested in understanding these phenomena, and it's really important for interpreting collision data in terms of the fundamental quantities. So in terms of understanding what's going on at this high level theory, you run these simulators. And there's a nice survey on event generators by a group of people who worked at the Large Hadron Collider. The goal that I'm going to look at here is, given this event simulator, we want to tune this event simulator, and this event simulator will have parameters. So our variables in this second part are going to be called parameters. And so parameters here is synonymous with variables. And we're going to tune it to fit data. So we're going to collect data at the Large Hadron Collider and then try to fit the parameters in these generators, in these simulators, to the data that we observed in practice. And then these parameters then allow me to make predictions. I keep asking our colleagues at Fermi National Lab whether if we make really good predictions, whether there's any chance we'll win a Nobel Prize in physics. And they always laugh at that point. So I'm somewhat disappointed. I'd hope to sort of become famous in some way here. Okay, so this is what the data and how the data is described in this community. The data is given by observables, and an observable corresponds to measured experimental data. So here on the right, the measured data are the black solid lines. And so they are in bins for a certain physics variable that's displayed on the bottom here. And in each bin, you make an observation. And the set of these observables is called S. It doesn't really matter. One way of thinking of an observable is that it is displayed as a histogram. But really, each of those is an independent physics variable that you have that you want to fit to. And we call each of these values, we call them, or the parameters that correspond to them, we call them bins. So there's each observable has a number of bins. It's actually easier to put this into mathematics formulation. So what we have is a Monte Carlo simulator, and I call this MC of P. And P are the parameters. So these are the guys, these P are the ones that we want to find, that we're interested in estimating. And so for each bin, we obtain experimental data, RB, that's the data from the experiment. And we also obtain the uncertainty. The physicists also tell us the uncertainty of the experiment. So these are these guys over here. And then we somehow have this simulator. It's a black box function that for any value P that I input into the simulator, I obtain an output of the Monte Carlo simulator for a particular bin. And I also obtain an estimate of its variance. And I should say that the variance here is actually very boring. It's homogeneous. We looked at that, and there's really not much scope. And these terms, you can almost think of them as constant, but they're there. One of the challenges in this area is how to choose these weights WO, which are non-negative, that then define this nonlinear squares problem. And that is often done by preference. So the physicists have certain preference that they say, I like this observable that tells me more about the physics than others. And so you have a higher weight. We've been looking at using design of experiment ideas for actually choosing these weights. And it turns out that allows you to often choose them automatically. Typically, they're chosen by the physicists. And I'm just assuming that these weights are given here. So we're not going to optimize the weights. So the goal then is to minimize this chi-squared residual. It's a nonlinear least squares problem. Unfortunately, there's no derivatives available for either of these two functions. So we don't have gradients. The functions are noisy, and I'll show you towards the end. I'll give you an example and show you how noisy these functions are. And you can think of, ideally, if you have enough time, you can evaluate these functions to very high accuracy. But that means running a lot of events. Events are particle collisions, and you have to run tens of millions or billions of events in order to get a reasonable number for these uncertainties. That makes it very expensive. So even running at just 1 million events or so, which doesn't give you a lot of accuracy, the cost is still something like 13 CPU hours on a cluster. So the evaluation here parallelizes by bins. It also parallelizes in terms of the random parameters that you throw into your Monte Carlo simulator, or sorry, the random variables that you throw into your Monte Carlo simulator. So you can do this often relatively quickly. We've been looking at applications where we have 7,000 bins. So there's 7,000 terms in this double sum. So there's 7,000 nonlinear equations, if you think about it, but there are only 14 parameters. So this is hugely overdetermined problem, sort of factor 50 in terms of, actually factor 500 in terms of parameters versus equations. It's hugely overdetermined, and it turns out there's a lot of redundant information. So sometimes some of these observables actually have repetitive or similar information. There's a tool for doing this called Professor. That's the classical approach, where you randomly generate a set of parameter values, pk, at which you evaluate the Monte Carlo simulator for all of the bins, and then you fit a cubic polynomial to these observations. And you then do a one-step optimization where you minimize a surrogate and just solve still a nonlinear least squares problem, but for a fixed, instead of the Monte Carlo simulator, you simply have your surrogates in here, and you return those as the optimal parameters. And that's the tunes that I talked about, the Monash and the A14 tunes. That's what they do. Most of the time is then spent on arguing what weights you take and then solving this optimization problem. So with our colleagues at Fermi, we've developed Apprentice, sort of in, well, which is extending Professor. The goal is to run on high-performance computing platforms. And we're also looking at developing surrogates that are more suitable for physics simulations. So in particular, I talk about that in a moment, rational approximations. And what we've been looking at recently is then embedding these surrogates within a trust region approach. It's kind of obvious if you're familiar with trust region methods, then really what you want to do is you want to put a loop around this simple idea and simply iterate and refit and do some kind of trust region approach or line search approach that allows you to then get optimal parameters, not just for this surrogate, but actually for the original function MC. That's what we're after. And so that's what will come at the end. So I'm going to talk a little bit about rational approximation, because I think this is a really neat idea, and it is also related to semi-infinite programming, as it turns out. So typically the models that we use, and I've dropped the denominator here simply because it's not that interesting. So there's no denominator in this expression here. So the surrogate models that we use are typically cubic approximations. So if you think about that, that's actually quite a large cubic for a 14-dimensional problem. That's a lot of information, a lot of data points that you need for that. And we talked to a physicist and he said, well, rational approximations would be good, but when we're doing optimization later on, we want to make sure that we can still minimize, and we don't want poles in our rational approximation because they're going to make the optimization a lot harder. And so in order to do that, we looked at some new ideas on how to construct PullFree rational approximations that give us better approximations of the physical laws. And in particular, we're looking at a way of constructing not just a polynomial, but actually a rational function. So that's a quotient of two polynomials, obviously, that approximates our Monte Carlo simulator. But we want to make sure that we don't have poles because we're using those in an optimization setting. And so the approximate subproblem that we're going to solve, and I'm just making the notation a little bit easier here. I would like to approximate a nonlinear function f using a rational function that where I have a numerator and a denominator. And I have some points at which I've already evaluated my nonlinear function. And so the problem can be written as a least squares problem, again, a nonlinear least squares problem here, where I'm just looking at the error between my rational function and my function that I'm trying to approximate here. And I just take the least squares error subject to my numerator being a polynomial of degree n in m variables, and my denominator being a polynomial of degree m also in m variables. And it turns out there's a simple trick. Everything I'm doing is simple, I should add. If you could just multiply through by the denominator here, then your least squares problem is much simpler. And in fact, this is now a linear least squares problem, right? Or at least it's a linear, it's a linear least squares problem because the coefficients are linear, or these expressions here are linear expressions in the coefficients of the polynomials. So that makes this a linear least squares problem. Unfortunately, there's also a trivial solution, and I'm glad nobody piped up and said it, because you can just set both the numerator and the denominator. If I set this to 0 and I've set this to 0, then I square that and it's 0. And I know that that is a global optimum of this problem. And so I've just solved the problem, but that's not a very interesting solution. There's one approach that's based on linear algebra, the Sequential process for orthonormal polynomials that you can use. There's been some work on doing rational approximations in the 1D case that goes back to a number of people. And that can be extended to higher dimensions. It turns out it's not guaranteed to avoid poles. So instead, it actually turns out it's better to think of this again as an optimization problem. One of the reasons why the one-dimensional construction doesn't generalize to multiple dimensions is because the poles in many dimensions are no longer isolated points. They can actually be sort of hypersurfaces. So here on the right, I'm showing you a contour plot of a rational function. And this rational function has poles where the red lines are. So these red lines are not just isolated points, which makes it harder to get rid of them. And so we thought, well, this is a perfect way. We can add a constraint that says R of P, our rational function, has no poles. That's equivalent to saying that the denominator is non-zero in D, but that's a terrible constraint because that's an open set. And so we can say it's equivalent to saying that D of P does not change sign in D. So it's either positive or negative. And so without loss of generality, we just find a lower bound on the denominator. And we ask that this denominator is sufficiently positive. You could have chosen negative as well. And everything goes through. So then here's the optimization problem that you need to solve in order to find a pole-free rational approximation. And that's again a semi-infinite optimization problem, or you can think of this as a robust optimization problem. I want D of P to be greater or equal to tau for all P. So it has got the same structure that our robust optimization problems have. This problem is, again, a nice problem, provided that if D of P is an affine function in the uncertain parameters P, then I can use the same LP duality trick that I showed you in the last talk and rewrite this as an LP, as a linear set of constraints. This is an affine set of constraints with a quadratic objective. So it becomes a QP, which is kind of cool. But we're interested in higher dimensional functions. And so we have this little algorithm, which is motivated by Polyak's algorithm. In fact, it's just exactly the same algorithm. We start off with a relaxation where we have a number of points, pk, and we ask that for the first capital K points, that's our fitting problem. And then at the remaining points, at those points and the remaining points, we enforce this constraint. So we only enforce this constraint at a finite number of points. So it's always K plus L points. Now, one question might be, natural question might be, well, why don't I take this L and add it to my fitting here? Because that would be presumably a better approximation. But then I would have to reevaluate my function f here, and that's expensive. So I don't want to do that. I just want to use these auxiliary points to make sure that I don't have any poles. And the algorithm is very, very simple. So you solve the relaxation, you solve this problem here, up here at the top. And if you find the minimizer, and then you find for this new denominator that you now obtained, you then minimize the denominator over your domain. And so if the minimum here is greater or equal to tau, or is positive, in fact, then you're done. Then you have a PullFree approximation. Otherwise, this will give you a new point that you can add to your set of additional points that you have back here, and you can continue. And this converges slowly. It's got a linear rate of convergence, but it avoids having poles. There's one caveat here, and again, you can ask me, well, how tractable is this? You do need to find the global minimizer of this problem here, which is a nonlinear, possibly non-convex optimization problem. And of course, if this is an affine function, it's easy to solve, but in that case, we can just reformulate. Okay, so how good are these approximations? So we did a hypothetical physics experiment where we have a simulation that predicts how dark matter particles interact with a xenon-based detector. There's a process called direct detection. There are 3 parameters that we want to tune, so 3 P's. So we're looking at 3-dimensional rational approximations. And it's the dark matter mass, and then 2 couplings to ordinary matter. We use quite a high degree of this rational approximation. So we use degree 4 for this rational approximation. And we fit these rational approximations using 500 points that are sampled using a Latin hypercube sampling. So very simple standard ideas. And I'm going to show you the result in this plane of these interactions to ordinary matter. If we just compare the cost, I can run the full Monte Carlo simulator to show you, I'm going to show you a contour in this plane. If I run the full Monte Carlo simulator, I take 14,000 seconds. If I just run the rational approximation, then including these 500 points, I run at 288 seconds. So it's a huge improvement. I'm not entirely sure why we have different number of function evaluations there to do the same thing. And so here's the picture, and this is really quite revealing. If on the left, we have the full simulation. So this is evaluating the full Monte Carlo simulator. And it shows you the contour plot of the log likelihood function. And this is the function that you then want to maximize. So think of this as the maximum of this function tells you something like physics. On the right here, you have what you get from a cubic approximation. And so you see some of the same characteristics, but not quite. And then if you use a rational approximation that may not avoid poles, you get this. And if you use our rational approximation, you get something that's almost indistinguishable from the true physics. There's some differences, I think here. There are some differences, but they're sort of hard to see. So this is kind of cool. That tells you that if you want good approximations and if you're optimizing a very expensive function, then maybe it is worthwhile to go for approximations that are a little bit more expensive to compute, but that provide more information and have better approximation properties. So now, in the last 10 minutes or so, I'll tell you a little bit about the trust region framework for optimization under uncertainty. So just to remind myself as to where the problem that I would like to solve, I would like to solve this chi-squared minimization over the Monte Carlo simulator. So my physics simulator, this MC of B. And the values that I get, if I want to evaluate this function, then they are the mean and mean variance of an MC simulator. But I actually never see those values. I cannot evaluate that. All I can do is run my event simulator for a finite number of events and get some approximation of these values. And I can control the approximation quality essentially by controlling the number of events that I put into my Monte Carlo simulator. So it's the number of particles that I'm tracking in my virtual experiment. There's no way for us to get gradients. It's not even clear that they exist, but we hope they do. And we haven't really checked that. And then over here is the data that's given from the physics experiment. So we're given the data from the physical experiment. And the goal then is to find at least a local minimizer of this chi-squared residual here, and that hopefully that tells us something about the problem. And so the first step then is to replace this expensive function for which we don't have gradients by our rational approximation. So that's the first step. We use a smooth approximation, and in our case, we use a rational approximation. And they're relatively cheap to compute. So that takes maybe on the order of 10 seconds to 100 seconds or so to compute for all of these bins and observables. So that's very efficient compared to the simulation time that it takes to actually evaluate these points. And so we have our regression models, and then we can control the approximation of our Monte Carlo simulator with this input variable or input parameter NE, that is the number of events. And I'm just going to ignore the variance in the remainder. I'm just going to delete that just to make my notation slightly easier. So please don't be alarmed if on the next slide you don't see that. And so here's a very simple sketch of the kind of trust region idea that we're playing with. We start off with a number of points, and we always have sufficient points that allows us to define our rational approximation. And we use a relatively small number of events in order to generate them. And we have some initial trust region radius delta L that we set. And then in our trust region iterations, we set up the regression model. So this is now replacing the nonlinear noisy function by this deterministic rational approximation here. And we minimize this inside the trust region. And I should have maybe changed the notation here. Yeah, we always have the trust region center is always the current best point. So this is not a good notation there. And then we compute the, oh yeah, that should actually be, sorry, I can fix that right now. It should be L, because L is the iteration index, and PL, and this is still not a good notation. It's probably K plus L here. That goes in there formally. And then given the solution to this problem, P hat, we compute the ratio of how well we do in the true function to how well we do in our model. So this is our model here, and our approximation to the true function, and we compare how well we're doing over this step. And that's a standard trust region approach. And if we do rather well, sigma here is something that's positive, then we accept the step and possibly increase the trust region radius. And now when we increase the trust region radius, we may have to resample because oh, that's not a very good trust region. Let's get rid of all of that. Let's see if I can draw a trust region. So if we increase our trust region from that, we move somewhere else, and we increase our trust region, then we don't have any information about points in other spaces. So what we need to do is we then need to resample in this case to cover this new trust region and the old trust region. And there's some bookkeeping you can do in order to make sure that you reuse the points that you've already evaluated. So that's important. It's much more interesting to talk about what happens if you reject the step, because step acceptance is sort of everything is going well, you're minimizing, you're going towards the solution, you're doing fine. When you're rejecting the step, it actually gets tricky. And it gets tricky because in traditional trust region, smooth trust region methods, all you would do is simply reduce the trust region. And that's all you need to do in order to ensure convergence for smooth problems. Because as you're reducing the trust region, you get agreement between your model, between your model and your original function. So the agreement that you have here, as you reduce the trust region, the steps will become much, much closer to the original point. And so this agreement will increase and you will eventually accept the step. Here you can't do that because as you reduce the trust region, you also have fewer samples inside your trust region. So you may need to change the sample size and resample. But you might also want to increase the fidelity at this point, because it could be that you're rejecting this step because you haven't really evaluated the true function here. So remember, this is the mean that we can't really evaluate, and it depends on the number of samples, how well we evaluate this. And what we have at the moment is a heuristic that looks at how the size of the trust region and the size of the gradient of this surrogate function to tell us how much more we need to evaluate, how many more evaluations we need to do here. But that's very much a heuristic. So here's a little bit of a picture. This is from a mini app that only uses 3 physics parameters. So it's a 3-dimensional problem. It's much smaller than the problem we want to look at. But it gives you an idea of how big the uncertainties are that come out. So if we have 10,000 events, which sounds like it's a lot of sampling, then these are the values that you get for your chi-squared once you form the chi-squared. If you change the number of events to 10 million, then you see that this is almost flat. So this is a huge difference, really. We, of course, want to work mostly in this regime because it's computationally cheaper, but we want to prove convergence about this regime or even higher regimes, because that's when we know we have a 0 gradient. So here's an output that Mohan got. And I really need to get Mohan to produce plots rather than numbers, but this is quite interesting, I think, still. So what I'm showing is the number of iterations. Delta K is the trust region radius. That's the projected gradient norm here. And so it starts off with around 2, and it goes to 10 to the minus 1. So it's not great, but it's okay. The next line here is the norm of the step. And then these 4 columns give you the rational approximation, the chi-squared of the rational approximation, and the chi-squared of the Monte Carlo simulator, evaluated with this many evaluation points. So the key part here is actually this is important. This is NE. And what you can see is we start with a relatively small NE of about 5,000, and then we crank it up to 1 million in order to get convergence. And the nice thing is that as you're rejecting steps, so this is the rho, this is the actual over predicted reduction here, over p ret, that's this value here. And whenever you see negative values here, then we're either reducing the trust region or we're eventually increasing. At some point, we need to increase. At this point, we're just decreasing the trust region radius, but here eventually we increase the number of samples. And so this is this interplay that we've started to work on, which is not really, haven't figured out yet. The nice overall thing though, is that we reduce the Monte Carlo error from sort of 27 down to about 23. So we get about a 20% improvement by not just doing the one shot. So this is up here is what you would do, what classical people would do. This is the one-shot optimization. If we do this iteration, we get a 20% reduction, which I think is quite nice. Okay, and so we're almost at the end, allowing lots of time for questions, which could be a mistake. So there's, I've showed you in the second talk a parameter optimization problem for Monte Carlo simulator for high energy physics. This is really challenging because it's a noisy and expensive functions. We don't have explicit derivatives. And expensive here means hours of CPU time for a single function evaluation. The current approach here is a single shot surrogate optimization. You construct a surrogate, minimize the surrogate, and tell the user that's your optimum solution. And it turns out what we've been looking at is actually to use a trust region approach here to improve on that. There's some interesting things. You can reevaluate the Monte Carlo simulator at the same point, and then you can combine the statistics. There's a way of combining the statistics, so you can crank up the NE at previous points, the number of evaluations at previous points, which is nice. And so we're looking at the interplay of the sample fidelity, the sample size, and the trust region radius, which is kind of critical if we want to prove convergence. There's one big elephant in the room, which is that obviously we need a covariance matrix here. these measurements, they're not only correlated. There's more than that. There's sometimes causation. So sometimes you're measuring the same thing more than once. And so there's certainly work to do there. The goal is to eventually obtain an algorithm that has provable convergence guarantees. So, and maybe in a year or so, I can tell you about our success there. For now, I just want to thank you for being here, for still being here. I have no idea how many people are still here. And thanks for listening to my half-baked ideas. This is a bread that was baked in a microwave. And it bounces off the kitchen floor, which is great. It tastes not too bad, especially once you toast it. So once you've toasted it, it's pretty good. But don't bake bread to the microwave. That's maybe the main takeaway message from this talk. So thank you very much.
Thank you very much, Sven. So I will remind that I should not put bread in the microwave. I never tried to, so my takeaway is that do not try. But is there any more serious question? I don't see any question in this chat. Oh, yeah, there's one question from Yansu.
Hi, Dr. Leyffer. Just a quick question early on. I don't think I caught it, but just in one of the earlier slides, you're trying to fit the function using a rational approximation, and you say that there's a trivial solution of basically setting the functions as 0. Yeah, so here I guess I was just trying to wrap my head around this, and also about how to actually pick the tau on the next slide.
Okay, so the first question is easy, so I'll answer that first. So if I choose, okay, so if I choose n of p to be 0 and d of p equals 0, then in here I have 0 minus fk times 0 squared. And I sum this up, and that's 0. And I know that a lower bound, oops, where am I? There. A lower bound on this least squares problem is 0.
Mm-hmm.
I just showed you there's a feasible solution that those are certainly polynomials of degree m and n. They're very special polynomials. And the residual is 0. So I have a lower bound that's 0. I have an upper bound that's 0. Therefore, I have an optimal solution. It's a very, but of course, it's not a PullFree one, right? Because this denominator is 0 everywhere. And then choosing tau is tricky. And this was sort of hidden, and I didn't talk about it. It affects the scaling, because depending on how you choose tau, what you're doing is you're looking at a rational function that's numerator of p divided by denominator of p. And so depending on what you choose for d of p, if this is just greater or equal to 10 to the minus 6, then this one may have to go to 10 to the 6. So you want to have good scaling here. And I think what we found is that using tau equals to 1 works reasonably well. But you can stop the algorithm early. So this test here, this doesn't have to be tau. It just has to be positive. And so as soon as it's positive, you can stop. You don't need to push it beyond this bound. And so, yeah, I don't know if that answers your question. It was a bit rambling.
Yeah, that was helpful. I was just thinking, and again, I'm also just thinking out loud. Instead of constraining the value of the function d, could you constrain the structure of the function?
Yeah, of course you could. Oh, you're smart. Okay, so here's a nice problem. Okay, you know of what's it called, positive polynomials, right? Or sums of squares polynomials. Mm-hmm. So if your polynomial is a sum of squares, then you know it's non-negative. So if you just add 1 to it or a small constant, then you have a positive polynomial. So an interesting question would be, yes, that's much better if you can somehow, rather than doing this constraint here, you choose this space of polynomials from which you choose your function, and then you don't need this constraint. You get it automatically, and that's a much smarter way of doing it. And I think if you do something like sums of squares or things like that, that also has semi-definite relaxation. So I think that's a very interesting idea.
Awesome, thank you.
I can send you some test problems if you want to work on this. So.
Thank you, Sven. Other questions? Eric? Eric, you are on mute.
Yes, I'm back to my tractable question. So it's not to judge about like being fussy about complexity theory or whatever. It's I'm wondering like what type of problem have you looked at that you you have a feeling that you can solve this equality constraint easily. I just feel like perhaps we don't have the same tools to solve problems, and I could learn from this. Because when I deal with it, just for an example, typically I try to use h of x as being a vector composed of convex function. And then I will actually impose that the uncertainty set is non-negative, so that
Okay.
Your inner product U transpose H is a convex function, and then when you apply these tricks, you do have an inequality. You'll have H of x greater or equal to B transpose gamma. So I'm wondering if there's, I mean, if you've looked into, I mean, you talked about portfolio optimization. Do you have an example in mind of?
So for portfolio optimization, this, I believe, in the portfolio optimization problem, no, this is a quadratic. This is still a quadratic, so that doesn't help us. And you're right, I haven't looked at under what conditions this problem is tractable. Okay. And this is actually worse because this is a dirty trick, right? You can have an original problem. If I go back here, if this problem could actually be convex. I think that's what you were saying, right? This could be a convex constraint, provided that U has certain structure. If U is non-negative and H of x are convex and B of x are concave, then this is a convex constraint. But when I go to my reformulation, it becomes non-convex. And so we're losing something. That's right in that case. And we're taking a convex problem and we're making it certainly into a non-convex problem. And I don't have a good answer as to how to handle that.
Well, there's some nice duality trick you can use to preserve the structure when you, so you take your polyhedral set, but then you intersect it with the space that is needed for convexity to happen. And then in the dual, you can make it appear again.
Oh, right. That's interesting. Do you have a reference for that? Or do you just want to write your own? You can just write your own paper and tell us how to do it. That'd be good too.
I mean, we can talk about it offline, or
Yeah.
I'll try to. There's a paper I would simply send you regarding these nonlinear robust problem that could be helpful there.
Yeah, that'll be great. Thank you.
Otherwise, you showed this conversion of the difference between the rational function, the error with respect to the rational function, and then you multiply by the denominator on both sides. This is not an equivalence, is it?
This part down here.
Yeah.
No, it's not.
Okay.
And it's not an equivalence precisely because of this issue here. Because this solution is not a solution of the original problem. So if I have, well, it depends what 0 divided by 0 is, how it evaluates. But even if it evaluates at 1, it's not a 0 residual in general, right? You would have, in this case, you would have 0 divided by 0, but that's not the same as the 0 you get here, 0 minus 0. So it's not equivalent in that sense.
To me, it seems like in your reformulation, you're reweighting the different points differently, because you could also have a 1 over d square, I guess, in front of that expression.
I could, yes, yeah.
To make the two objectives equivalent.
Yeah, that's true.
Okay.
Oh, that's an interesting point, yes. But then I lose the fact, what's nice about this is that this is a quadratic. This is just a quadratic in the coefficients of these polynomials. So the coefficients appear linearly in the polynomials, and then it becomes a quadratic. So that's nice. Cool.
Eric, more comments, more suggestions? No? Anybody?
Anyone else?
Anybody else? I don't see anybody else. So maybe I have a few questions too. Maybe not as good suggestion as Eric, but I'm a bit curious about simulators that you have, because you said that it's a Monte Carlo simulation, but my first question is, how much control do you have on the simulator? I mean, once you call the simulator, is it really an oracle when you have no control on it? Or can you expect from the simulators that you can fix the Monte Carlo rules, and so you can use command random numbers? And the point, in my opinion, is quite important in the slide 18 when you use translation methods. When you compare with respect to the true functions. So when you compare the true function with the Monte Carlo simulation at 2 different points, the question that I have is about how do you control the noise between the 2 points? If you can use command random numbers, you can reduce the noise. But if you are only able to do independent random numbers, it's more difficult.
Okay. So I believe we can set the seed. So that means between different points, they could use the same random numbers. But I'm not really sure how much control we have over. I didn't do the coding here, so I don't really know how much control we have over the Monte Carlo simulator.
Yeah, but if you can set the seed already, you have command random numbers, and the variance of the difference will be much less than if you use independent random numbers.
Yeah.
And possibly if you can go deeper in the simulator, but you have to discuss with the physicians that have developed the simulators. Maybe you can use synchronizations ideas. I mean that you use streams of random numbers separately for all the random variables. Then you can try, because you want to be sure that the predicted decrease from your targets is really comparable to the decrease of the true function. So the true function is noisy, so that can make some difficulties.
Yeah, we should look at that. That's an interesting point.
Another question still related to random number generations is that you mentioned that in your small example that you generated the probability using Latin hypercube sampling. So did you consider to use randomized Latin hypercube sampling in order to evaluate the quality of the final solution?
No, we didn't do that. So we only have, no, we use a very simplistic sampling strategy, I think. So you're saying randomized?
Randomized Latin hypercube. It's a very easy trick to randomize some quasi-Monte Carlo points in order to be able again to define some confidence intervals. Of course, in these settings, you have to be careful because you have an optimization bias too. You can have some overfitting, but I'm curious.
No, we didn't. We use very simplistic sampling strategies. The only thing we did for the rational approximation was actually we found that it's important to sample on the faces of the hypercube. So you want to make sure you have samples that lie on the boundary of your feasible set, which is basically this cube here.
I see that can make a bit randomization a bit more difficult.
It does, and so we basically kind of divided it. We divided the budget up into two parts. One, everything that's evaluated on the face, and then everything that's evaluated inside the hypercube. And the reason for that was because we found that if we didn't do that, we would find poles near the boundary. So you sort of make it pole-free, but you kind of need to make sure it's pole-free everywhere. And so that's why we needed points that sit exactly on the boundary. That was when we generated the rational approximation. But it's not random. Well, it's a different kind of random sampling in that case, I guess.
Yeah. But I still have other comments, but I see the time, and we can we'll open the breakout room, so we can, if you're interested, people that are interested can continue the discussion after on the breakout rooms. But since it is already 3:30 and it has been already a long week, I do not want to stay too long with my questions, especially since some person can find the question quite boring. So I will just take the time and I will give the word to Eric and Walter after to thank all the speakers. It was not exactly the way we had in mind the workshop, but when we start to settle the workshop, because we expected to be able to encourage the discussions inside. But still, this solution, that even if it is not perfect, I'm really glad to see how successful the workshop has been. I've been very impressed by the quality of all the talks. So I'm really glad that this workshop, even this form, has been able to be proposed. I hope that all the participants and speakers has also enjoyed the workshop. And I will say that I want to also congratulate and thanks a lot my colleague Eric Delage and Walter Gray, that it must work many more works than myself, so they really deserve all the congratulations. And First, I want to thank all the speakers, because without the speakers and all the quality of the talks, the workshop would not have been such a successful event. So thanks to all of you, thanks to the speaker, and to the attendees, and Rick will be able to comment more about participation.
I just thought I'd share with you some statistics about the registration as a concluding remark, that we had over 300 participants to the workshop from many different countries. So thank all of you for finding the time in your busy schedule, to attend and to present. As Fabien said, this would not have been possible without the keenness of all the presenters to answer positively to our invitation initially, and then accept very naively to postpone their visit or their presentation to an unknown date in 2021. So we're really proud and happy of the results of all this. Just to announce on what's coming up. So this is part of a more general thematic program, the mathematics of decision making. And if you have still some free time in your schedule in November, the following program the following workshop is on agents, behavior, and combinatorial game theory. So this might be of interest to some of you. It's organized by Margarita Carvalho, Patrice Marcotte, and Sylvia Papai. And finally, I take the opportunity to share with you information about a recent journal that appeared It's steered by Dimitri Bertimas, Martine Labbé, Eva Cayley, and Marc Teboul. The goal of the journal is to be able to offer an open option to our publications. So you can find the website of the journal by following this URL or the QR code. These days it becomes more and more important to make our work open and so that it's easily accessible by the public. So I thought it was a good opportunity to share with you this initiative. Walter, do you have some final words to say?
No, simply to say, I mean, I'll parrot what Eric and Fabien has said. So thank you very much. First to the presenters, the colleagues that presented, then to all the attendees. I mean, ending the week, I think this was a success, at least for my part. So I hope that everyone enjoyed it, and hope to see you soon in person. So let's hope next time we'll be in person.